Now, in the second part of the lecture, we need to repair the freely joined chain model in order to comply with the data. And here we will use the intuition that we obtained from the earlier rod model of the DNA that involved a persistence length at which DNA is basically stiff, where the persistence length is longer than the typical length scale, the distance between two units in our simple model. So let's look back on the real structure of the DNA. So we know the DNA is a helix, where the helix is characterized by a twist or turn, which is given by 10 bases per turn. So every 10 bases, we come back to the same position on this helix. Now let's incorporate this knowledge into the microscopic model that we made up. So in the microscopic model that we made up, we had the energy per site, which is given by epsilon I, is given by minus F times L times sigma I. Now, a very simple way in order to characterize that we have this helical pitch of 10 bases per turn, we now just add an interaction between neighboring nucleotides or particles on this one-dimensional stretch, characterized by an interaction energy gamma. Hence, epsilon I now reads minus FL sigma I plus gamma sigma I times sigma I plus 1. Hence, with this, the total energy of any configuration is equal to sum on all I epsilon I, which is equal to sum on all I minus FL sigma I plus gamma sigma I plus 1. Now, seeing this total energy, we realize that this energy, or the Hamiltonian, is that of the 1D Ising model. In order to calculate the mean extension of such a system, we use exactly the same ideas as before for the freely joined chain. So we calculate the canonical partition function, and from there go on and calculate the observables. Now, the canonical partition function of the 1D Ising model we solved exactly in statistical physics, and just to remind you, there we used the eigenvalues of the transfer matrix that characterizes the different energy values for sigma I and sigma I plus 1 equals to plus minus 1. So the 2x2 transfer matrix is a combination of factor of e to the power plus or minus beta FL plus or minus gamma. The eigenvalues of this transfer matrix, lambda plus minus, equals to e to the power beta gamma times the cosine hyperbolic of beta FL plus or minus square root sinus squared beta FL plus e to the power minus beta gamma. Now, for large length scales, so large number of n, the n-particle partition function is given by z of n, beta, and f is equal to lambda plus, so the positive eigenvalue, to the power n. Now, the way how you come from the Hamiltonian to this particular partition function, you might want to look back in the extra clip that I put on Brightspace, where we solved the 1D Ising model exactly. So having the partition function, we now can calculate the mean extension. Again, the same log derivative trick. So the mean extension divided by the maximum extension, n times L of the chain, is equal to 1 divided by beta, partial derivative with respect to the force of the log of the n-particle partition function. Now, doing all these derivatives you come up with, again, the same result that we obtained for the Ising model, that the mean extension is equal to sine hyperbolic of beta FL divided by the square root of sine hyperbolic squared beta FL plus e to the power minus beta gamma. At last, we looked for two special cases. The first is that we switch off the interaction. Hence, we should obtain the same result as we obtained for the freely jointed chain. And indeed, this is the case. In that case, the square root is then just given by the sine squared of beta FL plus 1. So the exponential factor is just kicked out. And the square root of sine square plus 1 is equal to cosine hyperbolic. Hence, we come back to the result that we obtained for the free chain. Another interesting result we obtained for small force. For small force, or actually for small beta FL, the sine hyperbolic can be interchanged to just its argument, and we obtain that the mean extension, z, divided by the maximum extension, n times L, is about force divided by kBt times L divided by e to the power minus beta gamma. Now, on one hand, this gives exactly the same result as we obtained for the freely jointed chain, namely that the DNA behaves like an entropic spring where the spring constant scales with the temperature. On the other hand, it tells us a microscopic interpretation of the persistence length. Here we see the factor of L divided by e to the minus 2 beta gamma. Hence, the interparticle length L is modified by the interaction energy e to the minus beta gamma. For large interactions, the length scale is increased. That is exactly what we were after in interpreting the persistence length. Yet here we derived a microscopic model in order to understand what the persistence length is. So what did we derive today? Well, we wanted to explain the force extension curves of DNA that has been shown, for example, in the experiment of Bustamante. We realized that we were able to interpret the DNA, which is a very complex molecule, just as a stiff rod, and interpret the data in those ways. Yet what we had to introduce here is a certain length scale, which was called the persistence length. Now, in order to derive a more mechanistic and molecular model for this behavior, we developed a freely jointed chain model. Yet we've figured that the freely jointed chain would not fit to the data. Therefore, we introduced now in the second part of today's lecture in the interaction between nearest neighbor nucleotides, which describes the helical structure of the DNA. Now, by doing so, our model with interactions comes way closer to the real data. Yet there's still a gap between our result and the data, and that actually comes from our very simplified model that we made up. So we made up here a 1D model. Yet if you now would extend this model for a 3D, in which you have to take also the angles that the different units in the DNA could assume, take those into account, you will come up to an exact model and mechanistic and molecular model of the DNA that really match the data. Yet the full derivation of such an extended model goes beyond what we want to cover here in our lecture. So in summary, we were inspired by DNA stretching experiments, which had been done 20 years ago, and we developed a microscopic model in order to understand those. For that particular experiment, we see there's a maximum length of the DNA that is just given by the length of the DNA stretch, and it's a non-linear behavior. The take-home messages of today is that this behavior and these experiments could be explained by the freely jointed chain model, where the extension in the freely jointed chain model is equal to L times the tangent hyperbolic of F, the force times L divided by kBt. Now, for very low forces, we see that the spring constant that can be associated to DNA is temperature dependent. That is called, the DNA is a freely jointed chain and an entropic spring. Yet to fully understand the data, we needed to also introduce more detail in the structure of DNA, and that is coping with the helical structure. For that, we introduced an interaction energy between neighboring nucleotides given by a parameter gamma that characterizes that energy. For that model, which is equivalent to the Ising model, we obtain a modified force extension relationship, which I've written down here as a chain stretch. Now, the important part and difference between the freely jointed chain and this interacting chain is that we now have a microscopic idea what the persistence length of a polymer is about, and it's given by the interaction between neighboring partners. For chains which are shorter than this persistence length, L tilde is equal to L times e to the power 2 gamma divided by kVt. The chain is stiff rod. For longer length scales, it's a flexible polymer where just the number of polymer units and the length between the polymer units is modified.